Let's actually do the proof properly from topic 2, the last proof that we saw. Prove adjoint of a non-singular matrix is non-singular. Let's do it piece by piece. What actually is adjoint? A tiny concrete picture. You don't need to calculate it for this proof, but let's round it so it's not just a mystery symbol. So for a 2 by 2 matrix, the adjoint is basically this. um, D minus B minus C A. So basically what they did is they flipped um, from A to D and D to A, and I don't know what they did. They flipped crosswise and put minus sign to one of those diagonals. You swap the diagonal elements and flip the sign. Oh, you didn't, like, these are still B and C. The non-diagonal elements, their sign gets flipped, and for the diagonal elements they get swapped. So you swap the diagonal elements and flip the signs of the other two. For 3 by 3 it's more work using cofactor, but you won't need to build it from scratch for this particular question, so don't stress about that part right now. The key factor tool given to us like a formula sheet. So this formula, let's sanity check this with numbers you trust, so you trust it. This isn't required in the exam, just for your understanding. So for example, we have this matrix, then we find the determinant to be 1, and we find the adjoint. Now multiply the our matrix with the adjoint. Now what do we get? We get an identity matrix, which is exactly, and determinant of A times the identity matrix is also the identity matrix, so they match good. So the tool, this equation works. This is trustworthy. You'll just quote this as a known identity exam, no need to derive it. Okay, so we are still not deriving it. Fine. Why does this the step people get confused on? We start from this, so now take determinant on both sides. Whatever we do to the left side, we must do to the right side. That's just pure algebra, like squaring both sides of equation. So left side we take determinant. There's a ruler tool, just accept it. You multiply two matrices, then take the determinant. It's the same thing as taking each determinant separately and multiplying them. So this was not confusing. Fine, so this is the left side simplified, the right side. This looks confusing because these are two different determinant like things happening. Let's go down. So this is just a number. Determinant of A is just a number, a scalar, let's say 5. So I is the identity matrix. Example, we have this 3 by 3 identity matrix. So if we have a scalar multiply with identity matrix, just means multiply that number to every entry of the matrix, so it becomes this. Now take the determinant of this matrix, a diagonal matrix with 5s on the diagonal. So and cross n. For a diagonal matrix, determinant equals product of the diagonal entries. So oh fine, so this is a useful information. Determinant is only equal to the product of the diagonal entries, so 5 cubed. Since it has 3 times 3, it was a 3 by 3 matrix and equals to 3, we got 5 raised to power 3, 5 raised to power n. Generalizing it, if a determinant of a matrix is k, some number, and the matrix is n cross n, then oh, this now like seems pretty obvious to me. Okay, so reason, scaling every row of n by n matrix by k multiplies determinant by k one time per row, and there are n rows, so you get kn. This is weird anyways. I got the idea. Putting both sides together, now it's simple. This was the part that was confusing me, this identity. Fine. Rest is all pretty simple. So using the exponent rule, we have this final conclusion. We now know that this equals this. Since this is not equal to 0, raising it to any power like n minus 1 still can't give 0. A non-zero number multiplied by itself any number of times never magically becomes 0. So that's why this now becomes 0. So this is also not equal to 0. Then this is not non-singular. And that's it.